Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
First of all, let me thank the organizers for giving me this opportunity. So in this talk, I will mainly cover several methods that are very useful for solving this semi-supervised structured output learning problems. But there are many methods, so due to lack of time, I will not be able to cover all of them. What I will do is I will take very few selected methods and then discuss about them. So my outline of the talk outline is given here. So basically the methods that have come for semi-supervised learning in structured output problems are in some sense either borrowed or adapted from the approaches that were used in binary and multi-class classification problem context. So first I will quickly review those methods. Then after that I will introduce these structured output problems in general. And then I'll make some observations in two sense. One is in terms of the methods that are adapted from the earlier simpler binary and multi-class classification problems. And the other one is structured output problem by themselves bring new challenges. So, or different aspects to the problem, right? Because that's the real motivation for coming out with the new methods for structured output problems. So in particular, I'll consider two approaches. One is these graph-based formulations and the other one is transstruction and related methods. The second type of methods use domain knowledge extensively. So at least from our experience, what we have seen is that if you really want to solve semi-supervised learning problem for structured output setting, use of domain knowledge is very important. Okay, and then finally I'll make some conclusion and some directions. Okay, just to motivate, this is a well-known thing. Basically, semi-supervised learning is motivated from the observation that manual labeling is expensive. However, it's easy to get unlabeled data. For example, in the web context, it is easy to get a lot of unlabeled web pages, for example, emails, right? It's not just that we have the unlabeled data, we also have some sort of domain knowledge or side information available with us. Here are a couple of examples. One is, let's say we assume that the training data distribution is similar or same as the test data distribution, right? In that case, in a binary classification problem, one can look at what fraction of positive examples exists in the training data set, right? For example, it may be 80% of the training data could be containing positive examples. Now, since the test data distribution is similar or same as the training data distribution, we can make use of that information in learning a better model. Okay. Similarly, in the semi-supervised clustering context, people have used in other information, such as, you can look at a bunch of examples or pairs of examples, right, which you would like to have them in the same cluster, or they should not be in the same cluster. And these type of constraints are known by the name must link or cannot link pairs of examples. But the point is that make use of unlabeled data with the domain knowledge or side information. So this really helps in constraining the solution space. In that process, you end up in getting the better solution. So that's the main thing in semi-supervised learning. To formalize, we assume that the input space is a d-dimensional real space, and the output space is typically problem specific. For example, in a binary classification setting, we have the label space as +1 or -1, which indicates the labels for the examples. And typically we have a very small set of labeled examples where xi denote the feature set of feature vectors, and yi are the corresponding labels associated with that. And we also have large set of unlabeled examples. As I said before, domain knowledge plays a crucial role, and typically they are specified by a set of constraints. For example, we saw earlier that 80% of the examples would belong to positive class, right? So that's a constraint, right? And then the learning problem is to learn a function g, which finds a mapping from the input space to the label space. A simple example is a linear classifier. Here w is the model parameter and x is the feature vector. Then using this function, if the value is greater than 0, we can say that it belongs to positive class, and if it is less than 0, it belongs to the negative class. So that's roughly the semi-supervised learning problem. A little bit of notation here. We'll be mainly dealing with the probabilistic models at the later part of the talk. So we denote w as the model parameters, and this log likelihood function plays a major role in the probabilistic model. Okay, and then to avoid the problem of overfitting, we also use regularization. So here we use L2 norm regularization, and this is parameterized by a regularization parameter sigma square, which is typically set using cross validation. And then the basic supervised learning problem consists of the objective function is specified by this, where you have the labeled data loss term and the weight regularization term here. Then the model parameter w is learned by solving this minimization problem. Okay. Now, so semi-supervised learning, to solve the problem, right? Basically, we cannot proceed further without making any assumption or make use of some information, right? So typically there are two assumptions that are widely used. One is the low density separation. For example, Chappell and Zion say in their paper that they make this comment. Basically, they say that we believe that cluster assumption is key to successful semi-supervised learning. Okay. In the classification context, what it means is that the decision function that we learn must pass through the low density region, right? That's basically what it says. So here is an example. So the leftmost figure, right? So it has two positive examples and then two negative examples, and these are labeled data what we have. Now if you build a SVM classifier, you will get a decision function which is the vertical line what you see here. Now if you overlay the unlabeled data points, right, which are shown by these cyan circles, you can clearly see that this vertical line cuts across this high density region. Now in this case we didn't use the unlabeled data. Now suppose if we had the unlabeled data, right, which are these points, and if we make this assumption of low density separation, then you will end up in getting a model which is the decision boundary which doesn't pass through this high density region. Okay, so that's the central idea here. Of course, one can also place this boundary outside this, still it will not cut across the high density region. So that's where this domain knowledge or additional constraint comes into picture. Okay, it's very important, right? Now in the probabilistic sense, this is same as saying that inferred labels of unlabeled points have high likelihood. What it means, for example, if you have a boundary like this, then the score for these data points will be high. Now if you are defining the probability using these scores, then it is natural to expect that they will all have high likelihood. That's the basic idea here. There are two popular methods which make this assumption. One is this transactive support vector machine, and the other one in the probabilistic space, there's a method which is entropy regularization based method. Okay, both these methods basically solve this optimization problem, where you have this objective function corresponding to the supervised learning part, and you have the loss term corresponding to the unlabeled data part. In the TSVM framework, basically what happens is that you solve this problem by doing alternate optimization. That is, keeping the labels y fixed, you solve for w, and then keeping w fixed, you update y. Okay, so in the update process, as I said before, these constraints are very important. So whenever you update y, you make sure that the constraints are satisfied. That's basically the idea here. Okay.
Do you change the labels of labeled data?
No, they are fixed. Okay. The second assumption is this manifold assumption. So here the basic assumption is that data points belonging to the same class lie on a manifold. Okay. Now, the manifold regularization, right, originally proposed by Belkin and et al., what they suggested was that in addition to the normal smoothness constraint that we have in building the model, we also have some smoothness penalty function corresponding to the marginal p of x, right? So, but then in practice, you typically don't have this density, any knowledge about the density function. All you have is the unlabeled data. Now, in that particular case, what they suggested was that you can basically approximate this density which is having a support of the manifold using the unlabeled data, and the manifold itself can be approximated using a graph constructed using that unlabeled data. Okay. So here is a picture which depicts that. Here you see this in this figure, this gray surface, what you see is the manifold, and these dark points what you are seeing here, they are the unlabeled data points. Okay. And then the graph is constructed basically by connecting these data points. So this connected graph makes the approximation to the manifold, and then what does that smooth penalty does? Basically it does that the function should vary smoothly on this manifold, and that is ensured by including a regularization term something like this. Okay. Basically this wij is the similarity or the similarity score or the edge weight which shows how similar 2 points are. Okay. And then so it's clear that when this edge weight is strong, we would like to make this gi closer to this gj, which basically means the function becomes very smooth on the manifold. That's basically the idea. Now that sum squared function, it's also having a close relation, right? So because this can be rewritten as a dot product of this function in the space, using L as the metric, where L is the well-known Laplacian function, right? So which is indicated by D minus W, where W is the weight adjacency matrix and D is the diagonal matrix, which measures basically the outer degree. Basically you sum all the weights in each row. That's basically what it is. Now Belkin et al., what they suggested was that, as I mentioned before, in addition to the supervised learning term what you have here, now you add this graph Laplacian based regularization term. Okay. So that's the basic idea. And then they had an interesting theorem which basically gives the expression for the many measure of this problem, which is shown here. And as you can see here, in addition to the labeled data points, you also have unlabeled data points. Okay. So the decision function is now determined both by the labeled and unlabeled data points. There are two popular methods which fall under this category. One is the Laplacian regularized least squares and the other one is Laplacian SVM. And these methods arise depending on the loss function what you choose here. If you use a least squares loss function here, you end up in Laplacian regularized least squares, and if you use hinge loss, then you end up in Laplacian SVM. Okay. So there are other graph Laplacian regularization based methods, so which directly try to estimate the labels of the examples directly on a graph. Okay. So here is an example. So in this example, we have constructed a graph where each node represents an example, and this edge weight represents the similarity between two examples. Okay. Now in this particular case, we have two examples belonging to class label -1 and one positive example, and the goal is to find the labels for these shaded nodes. Okay. Now if you use an objective function something like this, as I said before, if this edge weight is very strong, we would expect these two values to be closer, right? In this particular example, you can see that this edge weight is very strong, so naturally we will expect the label of this particular node to be +1. Similarly, you can see that the labels for these particular, these two nodes will become -1 and -1 and so on. Okay. But then, so this is only a background. So these are the two different popular methods, right? One is graph regularization based methods, and the other one is transductive SVM type methods. Okay. So now we come to the main part where our interest is in solving semi-supervised learning problem in structured output setting. Okay, that's our interest. To get started, so I have given three examples which are most popular in structured output setting. One is the hierarchical classification problem. So in this case, let's say you have k classes, but then they are not arbitrary. So they have some relations which are specified by a taxonomy tree. So in that taxonomy tree, the leaf nodes are the classes that we are really interested in. Okay. In multi-label, the other setting is the multi-label classification problem. So in this problem setting, a particular object can belong to more than one categories. Okay, so that's the that is this setting. For example, a document can belong to categories like finance and politics simultaneously. Okay, and the third problem is the sequence learning problem. So in this, one example is the input is a sentence, and what we are really interested is in tagging each of these words with the part of speech. Okay, so example is given here. The president came to the office, and then the tags will be determiner, noun, verb, phrase, and so on. Okay. Now there is so one of the important things to notice here is that in structured output problem, we can see that the number of output combinations that we will encounter will be exponentially large. For example, in a multi-label classification problem, where you have k outputs, where each output can take binary values +1 or -1, you can see that there are about 2 power k combinations, right? So this can result in making the inference really a hard problem. Okay. The other important characteristics is that it's not that like these output combinations can be anything arbitrary. Typically, there is a dependency between the different labels of the nodes that we see here, right? So in some cases, we'll be able to exploit this property to get better solution. Okay. Now, in terms of model, so in structured output model, we have the scoring function defined something like this, where W is the weight vector and F is the feature function vector. So one important thing to notice here is that here the feature vector is defined in the joint label space, both X and Y. Okay. Now, given the weight vector W, the inference problem is to find the label combination that gives the highest score here. Now, this can be a really hard problem because we know that the number of output combinations can be really very high, right? So, except for some simple models like a taxonomy or multi-label classification problem under certain assumptions. For example, Manik and Vishy had a paper where they had used the property of linear correlation to show that the joint output problem can be converted or transformed into an independent binary classification problem. Or it could be in the sequence learning setting, if you have a linear chain, algorithms like Viterbi decoding algorithm can be used to solve this inference problem efficiently. Otherwise, often it's difficult to solve this problem. Now, once we have the scoring function, we can define the probability model using their scoring functions for different label combinations. Now here again, as I said that log likelihood function plays an important role, right? Now, if you are going to write the log likelihood function for this model, it's easy to see that this partition function will play a crucial role. And then since we are having exponentially large number of combinations, evaluating this can become really nasty. Okay. Again, except for simple model like linear chain, I mean where it can be computed efficiently, training itself can become a nightmare. Okay, and the other aspect is that most of the training algorithms solve the inference problem and require the inference solver also, right? In that case, if the inference problem cannot be solved efficiently, again training becomes harder. Okay, so those are some of the challenges that you face when you come into this structure output setting. Now just to make some observations, as I said before, the reason why I introduced that graph based regularization method and the transductive SVM type methods is basically that those are the methods that people have really extended or adapted for structured output setting. Okay. Other aspects, I mean there are some important aspects that arise when we really talk about structured output setting. One is, as I mentioned, that computational complexity can be, I mean it's really a problem, particularly when you have large structure and the inference problem itself is hard to solve. Apart from that, there are other interesting aspects. One is, because there is a structure in the output, we can express our domain knowledge in terms of richer constraints. For example, in a multi-label classification setting, there may be strong label correlations that exist, which we'll be able to exploit to get better solution. Or in the information extraction context, right, where let's say we are interested in identifying the attributes in a publication record, usually there is an ordering of attributes, right? For example, author name occurs first before the title, or in a restaurant web page, you may find that name of the restaurant occurs first and then address comes next, right? So we can exploit these properties, and for example, some of these properties Raji will be explaining in his talk as well. The other important aspect is that by suitably selecting these constraint forms, it may turn out that the overall computational complexity of the algorithm can be reduced. Okay, so later we will see that how do we exploit these in one of our works. Okay, there is another interesting aspect, which is this partial labeling scenario. See, earlier in the binary classification problem, the labeling is a little more easier because you are just given a document and you need to say that whether it is a positive example or negative example. But now the moment you enter into this structured output setting, the labeling itself becomes harder, right? Imagine a tree which is having some 1,000 nodes, which is very common in the web context where you represent a HTML page as a DOM tree structure, right? So labeling itself is harder, right? So in that case, what typically happens is that you don't really get to label all the nodes in the structure. You may label only some of them, and then that results in an interesting scenario in structured output setting. For example, Manik was presenting the other day a multi-label classification problem where he had millions of categories, which is virtually impossible to, like get all the labels for a given example, right? So this introduces a new scenario in this problem setting. Okay. So now I move on to these two important types of problems. One is the graph-based regularization. So the first, the fundamental question to ask here is that what is a graph in this case, right? So in the binary or multi-class setting, what we said was that each example will be a node in the graph. Okay. Now here what we are having is the structure, right? Now how do I connect these two structures? Should I take the entire structure as a node in the graph? By the way, this graph should not be confused with the structure output itself, which itself can be a graph, right? So here the graph what we are talking about is that the one which we talked earlier, where each document is a node in the graph, right? So in this case, one can say that, okay, I have two sequences and I will represent each sequence as a node, and then I will connect these two sequences. Now some of the questions that naturally arise there is that how do I compare sequences of two different lengths, right? So that's one of the questions. Of course, there are several approaches that have come up in the literature. I will not go into all of them, but one of the basic approach that I will discuss about is due to alternate alt. Okay, And then these two subsequent works, basically they make use of this idea, but then this approach is computationally expensive, and essentially these two papers talk about how do you solve that problem efficiently. So I will not talk about these two papers, I will just focus on giving some background on this work. So here is an example. Let's say consider linear chain sequence, and then so one simple example is, okay, I have a sentence here, and then I associate part of speech for like tags for each of these words. So the basic idea what they proposed is that basically decompose this sequence into different parts. Okay, that's the basic idea, right? So, and then by parts we mean the following. If you really look at this sentence, right, in structured output problem, what basically people do is that you have some kind of feature functions associated with each of these inputs, and you also have these labels associated with them, right? As I mentioned before, the feature function itself is defined in the joint label space. Okay, so that's basically what is the characteristics of the structured problem. Now, one thing we can do is that we consider the label combination. In this particular case, the determiner and the noun, right? So that's one label combination, and then you can also have label combination like V and then followed by P, right? So that's another label combination, and you can also have other parts like, like where you use the input features combined with the label. Okay, so that's what is shown here. So basically, what is really done here is that this representation what we are having here, they are decomposed into different parts. One is horizontally and the other one is vertically, right? So this decomposition of the structure into different parts is the fundamental one. And then what Alton and et al. Argued was that use these individual parts that you see in the structure as the real nodes in the graph. Okay, so that's the central idea here. And then their motivation came from the observation that if you really look at the scoring function, what we saw earlier, can be really expressed as a summation of local scores of these parts. What it means, basically given a sequence like this, you count how many times a particular part occurs. For example, in this case, dt followed by n occurs twice, right? And then if I have a score for this part, dt and then n, so what is basically happening is that you have a weighted sum of scores of these individual parts. That's how actually the scoring function is computed, right? So that's the motivation for them to say that, look, overall scoring function is anyway computed using the scores of the local parts. So in that case, use these parts as the nodes in the graph. So that's the central idea. Then rest of the things follows basically the manifold regularization idea that we talked for the binary or multi-class classification problem. So I have rewritten the subjective function here. So as you can see that the first two terms, they are basically the objective function that you have in a typical supervised learning setting, and this term is again the graph Laplacian type regularization function. Okay, except that the nodes are defined using these parts, and then the summation runs over for all possible pairs that we see here. Okay, so in this case now this edge weight can be now defined on the part space. That's basically what that's how it is defined. Here again, as earlier, there is a representer theorem which gives the solution for the minimizer of this problem. Okay, that's basically what it is. So as I said before, the main disadvantage is that this involves matrix inversion, which grows with the data set size. So it's really not practical to use this particular method in the large scale setting. So next we move on to the other type formulation, where as I said that these are all like transactive type methods, and they use domain constraints heavily. Okay, how much time we have now? Okay, let me just quickly go through this. So basically we will consider constraints of this form, where basically it's specified by an inequality with some upper bound. Okay, And here, since we are dealing with unlabeled data, so this y is unknown here. And as I said before, selecting this constraint function in a suitable way helps in simplifying the computation. In this particular case, we assume that it decomposes over all the examples in the unlabeled data, right? So that's one. The other assumption is that this constraint function takes a form similar to the feature function. Okay, so these assumptions really makes the problem easy to solve, right? So they are computationally useful. Of course, one thing to note is that this form is not really restrictive. For example, in information extraction problem from publication record, these type of constraints can easily be used to specify constraints like average number of authors should be 2.5, or label journals should appear only once in each publication, and so on. One of the important things to note here is that these constraints, there are typically two types. One is instance level constraint and the other one is corpus level constraint. Okay, corpus level constraints, by that mean an example is that average number of authors should be 2.5, right? So in this case, we're not really saying that in each record the number of authors should be this much or something. Here we are saying on an average what happens. Okay. Now using that constraint model, now what we can do is that we can introduce a constraint penalty term, okay, using slack vector. Now what this slack vector does is that it measures the violation of the constraint, and what we can do is that we can try to minimize this slack vector, because in that process we will be minimizing the violation. Okay, that's the basic model that we consider. And then one of the important works in this area is the generalized expectation criteria method proposed by Mann and Matola. So what they did was that basically they added this particular regularization term to the supervised learning term, right? So now, so there are two things one should notice here. So one is, here the constraints are basically specified in an expectation sense. Okay, basically this PW is nothing but the probability model specified by the weight vector that you learn here. Okay, so in that sense what happens is that when you take a particular example, right, the actual constraint may not be really satisfied, because what this demands is that on an average that these particular constraints are to be satisfied, right? So that's one problem with this approach. And the other problem is that this approach is computationally expensive, because the gradient computation that we need while solving this minimization problem, that involves finding correlation between model and constraint features, and this can be really very expensive. Okay, now to address this problem, there are many works that you will see in the literature, but the most recent one is called the posterior regularization. So what they really did was that they introduced what's called an auxiliary distribution. Now what it does is that, and then of course as you can see that there is a new KL divergence term that comes in here. Okay, now so the advantage is here, right? So basically this auxiliary distribution, it decouples the constraints from the model distribution, right? So that's basically what it does. Now in this case the problem is solved as follows, right? So you keep Q fixed and then solve for W, and then you keep W fixed and then solve for Q. Now as you can see that only these first two terms are involved while optimizing W, and then when you are optimizing on Q, these two terms are, the next two terms are involved. So the main advantage of this method compared to the previous method, which is the generalized expectation criteria, is that it doesn't require expensive gradient computation, because you don't have to compute the correlation between the feature function and the constraint function. But then the disadvantage of constraints being satisfied in expected sense, it's still present. Okay. Then the Zayan et al., they introduced, when they basically extended the TSVM model proposed by Joachim's for the binary classification problem for structured output setting. Okay, but then there are some key differences from the generalized expectation criteria. One is we have this unlabeled loss term. Okay, that's one. And second is that these constraints are now specified directly. There is no notion of probabilistic or expectation sense here. So in that sense, one would expect the constraints to be satisfied much more, in a better way when you get a solution from this. But then this comes with other challenges. For example, this label space Y is exponentially large, right, for the structure output setting. But then this Zion et al. Basically what they did was that they worked in a large margin setting. In a large margin setting, what happens is that not all the output combinations are typically active. So what they do is that they maintain a subset of these label output combinations and then only work with that. That's basically what they did. Okay. So we extended this work, and then so what we said is that instead of working with that directly with that label space Y, right? So we basically introduced, we basically relaxed the problem and then introduced a label distribution on that Y space. That's basically what you see here as the variable A here. And then you can see that now the unlabeled loss term is defined using the distribution A here. Okay, and then the same thing appears here. Okay. Now this is again a non-convex optimization problem. Okay, and then so we need to be a bit careful in while optimizing such problems. Okay, so we took the approach of deterministic annealing. So where basically we introduce a entropy type term here with a scaling factor T here. So the basic idea is that you start with a very high temperature, okay, and then in the initial phase basically you allow this A to explore this entire area, right? Now, and then slowly start reducing this temperature. So in the deterministic annealing method, what happens is that once this T crosses some threshold, basically you end up in a region of good local minima. Okay, so as T tends to 0, you end up in finding a good local minima. Now, other thing to notice is that as T tends to 0, you finally realize, you see that this problem is same as solving this problem. Okay, so this deterministic annealing method is a useful tool to find good local minima. Okay, now from computational viewpoint, basically it is useful to use the solution obtained from the previous iterations at a higher temperature, right? So that helps in reducing the computational complexity. And then this problem basically you solve by as an alternating optimization, where keeping W fixed to solve for A and then iteratively you solve that. Okay, due to lack of time I will not go into details of these problems, solving this problem. Okay, so since I'm running out of time, I'll skip this part. But then I just want to make some final comments. One is in solving this semi-supervised learning problem in a structured output setting, right? So make use of as much domain knowledge as possible. But then one thing is that particularly when you are using this unlabeled loss term, what we observed is that if the constraint that we are using is not strong enough, the solution you get can be really bad. And this is typically one of the problems that is faced by everyone, and then everyone feels that TSVM method doesn't work. But our experience shows that if you use domain knowledge carefully, you can really get very good solution. Okay, and the other one is that use good optimization techniques, because all these problems are really having this local minima issue, right? So even though it is expensive, go for deterministic annealing type method, which can avoid this bad local minima. Now in terms of future work, there is a lot to be done here, because one thing in the structured output setting is that not much experiments have been really done to demonstrate the usefulness of these methods. For example, if you ask the question that should I choose this graph based method or a transductive SV method, it's still unclear, right? So one needs to do a lot of experiments on different types of data sets and then see for what type of data set which method is suitable. The other thing is that what type of constraints are more useful. Of course it is problem specific, but if you really want to gain something out of it, one has to choose this, use this domain knowledge to define these domain constraints carefully. Okay. The other problem is that computational complexity still remains a big issue here. Of course, nowadays everybody is talking about distributed computing. That's one option. But it would be better if one can look at the structure that is present in the constraints and then see whether those structures can be exploited to get efficient optimization algorithm. Okay. Last but not least, as I said, that domain constraints are important, but then this knowledge is not like accurate, right? So we may have some rough idea about it and then we try to use that. But now the question is that how sensitive is your method to this knowledge itself? Okay, there is almost no study or very little work that has happened in this area in the structured output setting. So these are some of the directions one can look at, and then we are still working on these problems. Yeah, so I'll stop here. Right.
Can you explain the problem?
Okay. Okay. So this is a taxonomy tree that we have here. Okay. And then in this particular example, we have 4 classes C1, C2, actually 5, C3, C4 and C5. Okay, so these are the class labels that we have here. And then these class labels are not arbitrary, but they respect this taxonomy structure. Okay. Sorry? Yeah, it's known in advance, right. That's right, yeah.
So it is only basically plays a role in the loss function?
Yeah, so you're right. For example, if I want to, if I'm okay with misclassifying the class C1 as a C2, but it will be more erratic to say that C1 is the same as C4, right? So I can use this taxonomy structure in the loss function itself, and then I can learn better model.
The others? All right, so we can talk later. So
Okay, thanks.